All right, now let's take a look at example 9, and this is where we start to kind of get into negation with predicates. And when we're negating predicates, there are rules, but it's actually kind of easier to think about it intuitively than it is with propositions and Boolean logic. All right, so let's start with a statement. How about our function r of x is x plus 2 is prime. We're going to begin with that as our starting function. Then we could make the predicate statement for all n that are members of the prime set. N plus 2 is also a member of that prime set. This is kind of an important concept I want you should be wrapping your mind around. You know, this is the function, and then this is the predicate statement. So the predicate statement involves a function, but it isn't just the function, because the predicate statement can be true or false. And we quantify the predicate statement. In this case, we're quantifying it with for all. So this says that for every prime, right, that's what we're saying for all n in P, if we add 2 to it, the result is also in prime. Well, then the question is, what would be the opposite of that predicate statement? What is the opposite is for every n in P, then n plus 2 is also in P. The opposite is that there exists some n inside the set of primes such that our r of x is false. We could also say there exists n that is a member of the set of primes such that n plus 2 is not a member of the set of primes. Okay? Two different ways of saying the same thing. The key thing that I want you to get from this is that the negation of for all is not for none, right? The negation of for all is there exists at least one example that for which this is not true. That's the negation, okay? So that being said, remember that a predicate statement and its negation cannot both be true. Only one of them can be true. Knowing that, which of these is true? Not obviously, but kind of obviously, the negation is true. So pick an example, you know, if you pick, say, 3, right? 3 plus 2 is 5. Well, in that case, both 3 and 5 are primes, so it's true. And then 5 plus 2 is 7, so that's true. But if you pick 7, 7 plus 2 is 9. 9 is not a prime. So there exists at least one prime, in this case 7, for which that is false. One other thing I'd like to point out from the book on the bottom of page 14, they mention that this symbol can also be used for such that. In my lectures, I'm going to not use that, but know that when you're reading the book, that symbol is in there. That's the kind of thing you should be adding to your vocabulary sheet. So the book will use that symbol at least once. I don't think it's particularly helpful, but it's out there. Okay, so that was kind of an intuitive example of how negation works when we're talking about predicates. This leads into the formal theorem 2. And in the formal theorem 2, D is a set of symbols. P is a predicate, and it's defined so that X is a member of D. Based upon those rules, the negation of for all X that are members of D, P of X is true, is that there exists X that's a member of D such that not P of X is true. And I'm running out of room here, but you know what I'm writing. So, for all X that exists in D, P of X is true. When we negate that, we just say that there exists some x in D for which P of x is false. And the other side of that is going to be the negation of there exists an x that's a member of D such that P of x is true, is that for all x that are members of D, P of x is false. So that is theorem 2, and this does somewhat change the other theorems that we've been working with for moving around Boolean expressions and propositional expressions, and that's why we're not going to do a whole lot with this, because it's really time consuming, and working the exists and alls through a statement can take a lot of time. You'll probably have to do one on the exam, so you should know theorem 2. But yeah, most of our work in this unit is really how do we take a human logical statement and write it out as a predicate statement.